So getting a bit more sophisticated, I have a trigonometric function here, and it is the case, sorry, a bit of the light. It is the case that I'm not going to be able to find x-intercepts. Well, maybe one's obvious, namely x equals 0. But here's an example where maybe it's a bit more sophisticated in terms of being able to find x-intercepts. Sorry, I'm just trying to manipulate the light. I've changed things in here. That's a little better. So if you don't mind me saying, can't we just treat this as a linear function, a line, y equals x, where I'm sinusoidally, gosh, I can't say that correctly, where I'm sinusoidally deviating away from that line, y equals x, with that particular sinusoidal function. And so would you agree that graphically speaking, here's a line y equals x. And if I sinusoidally deviate from it with a sine function, doesn't it behave something like this? And so if that's okay, just roughly speaking, and on a very intuitive level, then let's avoid finding x-intercepts. And let's just find out when I locally min and max out, and when I have inflection points. So roughly speaking, here's a graph from the obvious representation of its output. But now to differentiate, let's think of this. Now if you take a peek at that derivative, y prime equals 0 when the cosine of x is equal to -1/3. Now, one value for which the cosine of x is equal to -1/3 is an angle in standard position that's actually in the second quadrant, whose cosine is -1/3. And so that tells me we're going to get one of my local maxes. Even though I'm not building a sine graph, I'll leave that for you. And so I think this inflection point right here is that the inverse cosine of -1/3. However, due to the periodicity of this function, I think I'm going to get another one 2 pi units later. And so I will tack on, everybody, I'm running out of room. Can I just slide it over? I'm not going to change anything. Where's my eraser? Oh, there it is. So I'm not changing it, but sliding to the left a little bit. I think I'm suggesting that x is equal to the cosine inverse of -1/3 as I had, plus 2k pi for all k and z. And that's where I'm going to locally max out. I'm not going to write it because I'm running out of room. I think I'm going to locally min out at the next angle whose cosine is -1/3. Well, here's the first one in the second quadrant. The second one's in the third quadrant. And so I think when x is equal to 2 pi minus this angle plus 2k pi for all k and z is where I'm locally minning out. So here, and then 2 pi units later, 2 pi units later, and also in the other direction. Now to find the inflection points, I need the second derivative function, but that's going to be a piece of cake. Taking this piece right here and differentiating one more time is going to give me -3 sine of x. Which means the x coordinates of my inflection points are going to occur when x is equal to, well, let's figure it out. The sine of x is equal to 0 when x is equal to 0, but also when x equals pi, and then 2 pi, and then 3 pi, and then 4 pi. And so I think it's happening at all integral multiples of pi. So k times pi for all k instead of integers. So this may be at the inverse cosine of -1/3. This may be at 2 pi minus the same angle. But that inflection point here occurs at pi, and then another one at 2 pi, then another one at 3 pi. So I think maybe this example is not quite as nice as my last couple examples in the sense that I kind of relied on my intuition and basically understanding of sinusoidally deviating from a linear function, but at least I found the details. And if you don't mind, I didn't care about the corresponding y coordinates for this example.